So a deadlock is a cycle of transactions waiting for locks to be released by each other. And it's a classic problem in computer scheduling and concurrency control. And there's typically three ways of dealing with deadlocks: prevention, avoidance, and detection and resolution. Some systems don't do any of these things. They just use timeouts. So they'll just let transactions run for a while. And if the transaction doesn't do anything for a period of time, it assumes it's just in a deadlock and it aborts the transaction. And the danger of that approach, of course, is that you abort things that don't need to be aborted. Maybe they were holding a lock for a long time because they were busy doing some computation, and instead you aborted them because you thought they were just in a deadlock. Okay, so that's a sort of sloppy way of doing things. We're going to do things that are a bit more intelligent. Let's look at some scenarios where deadlock can happen. First of all, deadlocks are unavoidable in database systems. Sometimes they just happen. For example, transaction 1 might have had a query that wanted to read from object A and then read from object B. Transaction 2 might have had a query that wanted to update object B and then update object A. And those things happening in different orders simply lead to deadlock, and there's nothing the system could have done to avoid it. Now, another reason that we can get deadlock is if we implement lock upgrade poorly. So this can be avoided by doing the implementation correctly, but it's worth looking at. Look at this scenario. We have transactions T1 and T2 that are in the granted set in a shared mode. And transaction T2 wants to upgrade to an exclusive lock on A. So if we put T2 at the back of the wait queue, notice what's happening. T2 is waiting for T4, T4 is waiting for T3, T3 is waiting for T2. That's a deadlock. And so what we should do is simply implement this differently. When a transaction wants an upgrade, it should go to the head of the line. Now, if we do this protocol, T2 is waiting for T1, that's fine. But when T1 finishes, T2 can get its upgrade, make progress, and then T3 and T4 can run when it's done. So lock upgrades should always go to the head of the wait queue. Otherwise, you get a deadlock. Finally, if you have multiple lock upgrades, suppose in this last example that both T1 and T2 wanted a lock upgrade, at that point you have a deadlock again. And there's just nothing you can do about it, and you'll end up having to deal with that deadlock. Now, we can try to prevent deadlocks from ever happening. This is done in operating systems, and it doesn't work in databases. So in operating systems, the standard approach for deadlock prevention is to order the resources that you might lock. Typically, these are physical resources in the hardware. Like, you might need to get a lock on the screen to do a screen update, and then you might need to get a lock on the network card to send a packet, and you might need to get a lock on the printer to print a piece of paper. Okay? And if we order these resources, then your program, if it wants to do these three things, has to do them in that order. First, you would update the screen, then you would send a packet on the network card, and then you would use the printer. And every operation in the system would follow this resource ordering so that there's no way for deadlock to happen. All of these commands would sort of work their way down the resource order, and they would never have to loop around waiting for each other. Now, this is problematic for transactions in a database management system because we can't impose an order on the tuples or pages in our files. Basically, people can run queries in any order they like. It's a full-purpose, general-purpose programming environment, and we want people to be able to ask their queries in the order they like. And that's simply going to lead to deadlock. We can't prevent it by having a fixed resource ordering.